It's a great honor to be here and to see the birthday of Brazilian quantum mechanics or quantum biology. I would also like to thank Marcus for his wonderful presentation that will save me a lot of work to introduce this topic to you. And I, in fact, would like to talk about the puzzle of the cryptochrome quantum sensor, or because I do like to provoke the myths of the compass based on the radical pair mechanism. But first things first, the first thing certainly with a talk like this has to be, again, a European robin. And well, this robin, I think, is the only animal that is beloved both by physicists and biologists. And why is that? Well, certainly it is due to the fact that it masters magnetoreception that well. So that's obviously not to scale. How does it do it? Well, as we've just heard, the hypothesis, at least since 2000, is that within a protein called cryptochrome, a radical pair is being formed between, for example, oh, sorry. Yes, okay. Okay, good. So back again. So we have the cryptochrome, which is this protein. Oh, so okay, which is this protein? Well, which is the protein shown on the left, and which upon photoexcitation is thought. Okay, it's not going to work, I know. Okay, good. So I try once again. Okay, good. So okay, I lost my concept now. In any case, the story goes that within cryptochrome, an FAD cofactor is non-covalently bound. It can be photoexcited, which induces a cascade of electron transfer reactions, which give rise to the formation of a radical ion pair. This radical ion pair is formed between this FAD cofactor and one of the terminal tryptophans of this tryptophan tetrate. Initially, this radical pair is in the singlet state, well, because the precursor molecules are in the singlet state, which is this state here. However, this state can coherently interconvert between singlet and triplet states. Only the singlet state can recombine, which is indicated here as this back electron transfer process, whereas both the singlet and triplet state can form a signaling state. At least this is one of the popular models, which in fact is supported by in vitro results for EdCry, DMCry, and also the bird cryptochrome. However, other models have been suggested. For example, this model here, which relies on a reoxidation reaction where this FAD cofactor is fully reduced by two successive photoreduction steps to give the fully reduced form, which is this form over there, which is then reoxidized with molecular oxygen to form here this radical ion pair between the flavin semiquinone and the superoxide radical, which can again undergo this magical interconversion between singlet and triplet state and, well, possibly give rise to the magnetic field effect. Well, the model as shown here is popular. It has been suggested not only in the context of cryptochrome, but in the context of a lot of biological magnetic field effects. However, very likely, actually, I'm quite convinced about that, it would not work out due to the fact that superoxide has very strong spin-orbit coupling. So it's a tablet pi 1/2 species, which gives rise to fast spin relaxation due to the spin rotational mechanism. Well, in any case, we've already heard that all that is due to coherent singlet triplet interconversions. Don't want to say much more about that to save a little bit of time, but just point out once again the characteristic feature that most of this time, these radical pairs are in a coherent superposition state involving singlets and triplets, which is a magnetic field effect. It is the interconversion is driven by hyperfine interactions, but is perturbed by the external magnetic field. And if the singlet and triplet state give rise to different reaction products, this can eventually be seen in a reaction yield, which is what presumably the bird detects. This is singlet triplet interconversion gives rise to here this quantum beats in the singlet probability of the radical pair, which is directional dependent because the hyperfine interactions depend on direction. So hyperfine interactions and the directional dependence is shown here on the right. The one for the flavin radical is assumed to be, well, nearly optimal due to this large anisotropic axial hyperfine components here on the N5 atom and the N10 atom. To tryptophan, on the other hand, the partner radical, the presumed partner radical, is not that ideal. Well, can this be understood from a semi-classical point of view? Well, in principle, we can consider all these spins just as little magnetic moments that precess in the applied magnetic field. Well, not only in the applied magnetic field, but the effective magnetic field, which comprises the applied magnetic field, so the geomagnetic field, which is rather weak, and magnetic fields due to all the hyperfine coupled nuclei. This gives rise to this sum, the BF effective magnetic field, and the spin would then just be precessing around it. Something like that. So here the blue electron spin is precessing around the green effective magnetic field. And so do the nuclear spins, namely here shown for N5 and the N10 nucleus. So even with this very simple semi-classical model, very intricate dynamics can result. If we combine this now with a second radical, like the superoxide radical, the superoxide radical here on the left, you can see how singlet states interconvert with triplet states. So singlet states, which these two electron spins are more or less anti-parallel, states for which they are not. So in a way, a lot of these dynamics can in fact be explained on a semi-classical basis. And the question really arises, well, where is this quantum biological effect actually hidden? I mean, we all agree, as Feynman said, that nature isn't classical. And if you want to make a simulation of nature, well, then you ought to make it quantum mechanical. And, well, it's a wonderful problem because it doesn't look so easy. Well, but where is this quantum advantage actually hidden? Well, 2016, we have suggested that the quantum advantage can actually be observed in a spike here in the directional singlet reaction yield. Here, this is the recombination yield as the magnetic field direction is changed for very large coherent times. So coherent times, as you see, of the order of 10, 20, or 100 microseconds, a spike emerges here, which cannot be explained by the semi-classical approximations that I have just shown you a few slides ago. And this gives rise to a very spiky feature here, which upon axial averaging gives rise to this kind of geometrical representation of the anisotropy of the reaction yield, and then to spiky features in these visual modulation patterns that we have also already just seen before. Thus, in a way, the quantum description would allow the bird to navigate more precisely to kind of increase the accuracy of the quantum compass. Well, is there another indication? Well, very recently we have looked at tryptophan-flavin radical pairs once again of a very large complexity. So we've considered 12 nuclear spins in the flavin and 9 nuclear spins in the tryptophan molecule, and asked the question, well, if we reorient these two radicals with respect to each other, under which condition is the magnetic field effect maximal? And is there some correlation between this directional magnetic field effect and other well, fingerprints of quantum processes, like, for example, entanglement measures or coherence measures? Well, and the answer is shown here. There's a very clear-cut relation between an operational global coherence measure, which was introduced by Kai and Planier, and the directional magnetic field effect here on the y-axis, as is shown here for the flavin tryptophan radical pairs on the left and the flavin tyrosine radical pairs on the right. And in fact, this provides a clear fingerprint of quantumness already for relatively short-lived radical pairs. So for radical pairs that have a coherence time of only of the order of a microsecond. Well, okay, we don't need to talk about that. Let me kind of move to the more provocative part now. Well, the story goes that, in fact, I think this kind of presentation should not be started with a robin, but should be started with an elephant. And that's, in fact, the elephant in the room of cryptochrome magnetic reception. It's a very large and angry elephant, as you can see. And well, why is that? Well, the point is that radical pair mechanisms-based magnetic field effects are rather small. They're in fact too small to be currently measured by experimental approaches. So all experimental data so far have been obtained by relatively large magnetic fields of the order of a few millitesla. And directional magnetic field effects are even smaller. And in fact, we can make an information theoretical argument that shows that they're in fact too small for a bird to orient on its basis. So let me give you an example. For the flavin tryptophan radical pair, the anisotropy is of the order of 10 to the minus 5, whereby anisotropy is the relative change of the magnetic field over the mean recombination yield. Why is that? Well, the point is, in a real radical, we have 20 plus nuclear spins, and these 20 plus nuclear spins don't share common symmetry. And as a consequence, due to all these differently aligned hyperfine interactions, the anisotropy is drastically reduced, so it's of the order of only 0.01. Then, in addition, we have decoherence and spin relaxation, and this again reduces the sensitivity by a factor of 10. And eventually, there are interradical interactions, which again reduce the sensitivity by roughly a factor of 10. Thus, we end up with no more than 10 to the minus 5, which is, well, rather low, and begs the question of whether there could be some alternative mechanism that gives rise to larger magnetic field effects. Here, these are just a few examples where we have now recently looked at directional magnetic field effects in EDQI, so the cryptochrome from the plant, and bird cryptochromes, where we just see that, well, as we add in more nuclear spins, the anisotropy is really drastically reduced. And we also see that bird cryptochromes are by no means better than plant cryptochromes. So all this is very disappointing at first. Well, this here is on the point that, well, the electron spins are in fact coupled. They're coupled by electron-electron dipolar interactions. And the reason for that is relatively simple, namely the fact that we need to provide this back electron transfer channel. But this means that these radicals have to be close by. And if they're close by, then, well, they will be interacting by the electron-electron dipolar interaction, which is rather significant, namely of the order of 23 megahertz relative to the geomagnetic field, which induces Larmor precession at a frequency of only 1.4 megahertz. Thus, the electron-electron interactions are present, and unfortunately, however, they are suppressive to magnetic field effects. They are suppressive to magnetic field effects because they lift this first order degeneracy of the singlet and triplet states and therefore reduce the coherent evolution, which gives rise to weakened magnetic field effect. Yet, so far, they've always been neglected. And this is, for example, shown here. So where once again, we see this spike for a realistic model of the cryptochrome, and engaging electron-electron dipolar interactions, however, immediately reduces this spike. So magnetic field effects are basically abolished. So, well, what can we do about it? Well, we have thought about this for quite a while, and we have now kind of come up with 5 different models of how to overcome this suppressive effect, to modify the radical pair mechanism to end up with something that could work under practical, realistic conditions. And I've quickly summarized those here. The first idea is to just place a third radical close by to the radical pair. And this gives rise to an effect that we call D3M, so the magnetic field effect induced by the dipolar coupling between 3 radicals. And in a way, this allows us to compensate for the electron-electron dipolar interaction in the radical pair, and thus allows us to regain some of the sensitivity that we have lost. Then eventually, the second idea is to also place a third radical there, but this time allow it to react with the primary radical pair. And this gives rise to the so-called chemical Zener effect, which can boost magnetosensitivity quite dramatically. Eventually, we are now also thinking about systems that have internal degrees of freedoms that move. So for example, radical pairs that diffuse along a one-dimensional reaction coordinate, which allows us to utilize this quantum Zener effect to again boost magnetosensitivity. We've also considered harmonic driving of radicals, where the inter-radical distance is modulated, and eventually Markovian and non-Markovian open systems dynamics. Well, my intention is to quickly show you some results on the chemical Zener effect and on the driven systems. Well, a few words on the chemical Zener effect. Well, the idea is relatively simple. The idea is just that we start out with the radical pair of the form that I've shown you before and allow it to react with a third radical, which is indicated here as C. This third radical reacts with one of the reaction partners. In this scheme, it reacts with A to give rise to a secondary reaction product. This is indicated here as scavenged, this one here, whereas the traditional radical pair A and B can recombine back to the ground state. Now, in this scheme, the dynamics is no longer between a singlet and triplet states, but it is between doublet and quartet states. The interesting aspect is that the scavenging reaction, in fact, converts part of this population from the singlet to the triplet state in the initial radical pair, which requires us to model the entire spin triad on equal footings, meaning to extend the usual stochastic Liouville equation by terms that account for both all 3 radicals and both recombination processes. Well, I want to spare you the details of why this is working, but just show you how it is working. This is shown here, where the magnetic anisotropy is plotted as a function of the scavenging rate constant. On the left side, we have basically the situation of the radical pair, and on the right side, that of the 3 radical system. And as you see, if you choose this rate constant appropriately, the magnetic field effects can be boosted by more than a factor of 10, which applies for the relative anisotropy as well as the orientational spread. We've thought about several ways of how this could be implemented, one of which relies on the production of a long-lived tyrosine radical. In fact, in the bird cryptochromes, there is such a tyrosine residue here at the very end of the tryptophan tetrade. And the idea is that once this primary FAD tryptophan radical decays, it forms a tyrosine radical, which then sits there and waits for a subsequent photoexcitation to then do its magic. In fact, this could also be coupled with the reoxidation pathway that has been or is discussed that often, where the photo-reduced form of FAD is then reacted with triplet oxygen to give rise to this spin triad, which can give rise to much, much larger magnetic field effects, and in fact is robust to fast spin relaxation here in the superoxide radical. That's, I think, the only really realistic model for which reoxidation pathways could elicit magnetic field effects. So the success of this model is shown here, where, again, I just plot the magnetic field effect as a function of the weight constant. This works in the absence as well as in the presence of the electron-electron dipolar coupling. We'll skip that. And that's just showing you that all that is a very robust models. And by appropriately placing the third radical, we can elicit magnetic field effects of the order of, well, tens or of 40% again, instead of this very meager, I don't know, 10 to the minus 4 that result from the radical pair model. This is another idea of how magnetic field effects could result in the reoxidation. So this time, assuming that the fully reduced form of the flavin is oxidized by molecular oxygen in the presence of a third radical, which we assume is the s-coupled radical, kind of a radical that resides from a radical scavenging process. And in this model as well, very large magnetic field effects can be realized, which we applied recently for magnetoreception, as well as to explain hypermagnetic field effects on neurogenesis. Good, and eventually, I think my time is very soon up. I would like to say a few words on driven systems. This is a very recent work where we assume that there is some kind of harmonic driving between these two radicals, so that the interradical distance here is harmonically modulated. This modulates then the recombination rate, it modulates exchange interactions, and it also modulates the electron-electron dipolar interaction, but only by little. That is, assuming a fluctuation of distance of only 2 angstroms, which is a rather small modulation. The electron-electron dipolar interaction is only changed by roughly 3 megahertz, so by a very small contribution. And this model too can give rise to very large magnetic field effects, as is shown here, or here for different values of the exchange rate constant, whereby the interesting bit is that this results from the driving of non-adiabatic transitions between singlet and triplet states. So Landau, Zener, Stöckelberg, Majorana type of transitions, which allow us to repopulate population within this radical pair and make it susceptible to very weak magnetic fields, even in the presence of very strong interradical interactions. Well, I don't want to go into details. This also works for models that assume motion that is not that ideal. So for models where instead of harmonic motion, we use a Brownian harmonic oscillator, for example, whereby adding a little bit of noise turns out to even further enhance the effect here. Well, I think this brings me to the end of the presentation. My summary in brief is that the radical pair mechanism is certainly, well, the canonical model for weak magnetic field effects, weak strength magnetic field effects in the biological context. However, under realistic conditions, the predicted effects are really, really rather small, and we ought to look for alternatives. And I've tried to introduce a few of those alternatives to you. They rely on 3 radical interactions, and they rely on motion to overcome, in particular, the electron-electron dipolar interaction, which is an integral part in radical pair processes and cannot be neglected. Well, then, thank you very much for your attention.